Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Metal Oxide Semiconductor Field Effect Transistor MOSFET from the paper Semiconductor Materials and Devices. So let us see what we are going to learn in this module. First, the schematic of enhancement mode, that is E-MOSFET, will be discussed. Second, the detailed operation of N-channel MOSFET along with their IV characteristics will be discussed. Thirdly, we will study the construction of N and P channel depletion mode MOSFET. Lastly, we will discuss about the frequency limit for MOSFET. So students, let us start with a basic introduction about the module. MOSFET is nothing but the metal oxide semiconductor field effect transistor. It is a unipolar transistor acting as a voltage controlled device where current between the two electrodes, that is drain and source, it is controlled by the applied electric field at another electrode, that is gate. Here metal gate is isolated from the semiconductor by a very thin oxide layer. So let us compare a MOSFET with the JFET. So MOSFET can be operated in both depletion mode and enhancement mode, but JFET can be operated only in depletion mode. Second is that the MOSFET, they have high input impedance, thus small input current. JFETs, they relatively have lower input impedance. Lastly, the MOSFETs, they have higher speed of operation, that is, they respond instantaneously with a small change in the gate voltage, but instead of JFETs, they are relatively slower. Types of metal oxide semiconductor field effect transistors. So, the classification is based on the type of inversion layer. So students, as we can see over here, that is, if we have the N-channel enhancement type of MOSFET, which is normally off, the output curve, that is the variation between the ID and VD, is like this for the fixed value of VG, and the transfer curve is like this, that is, there is some threshold VGS is required so that the transistor becomes on. Next type is N-channel depletion type of MOSFET, which is normally on. The output curve is the same, but the transverse curve is little bit different, that is, it is normally on. So students, this shows the schematic of enhancement mode N-channel MOSFET. It has metal gate electrode which is electrically insulated from semiconductor, which can be N-type or P-type, by a very thin layer of oxide material, usually silicon dioxide. Gate terminal is isolated from current carrying channel, so no current flows into the gate. So you can see from this figure that it consists of a p-type silicon substrate onto which two heavily doped N+ regions, they have been diffused, namely the source and the drain. Metal contact is deposited on the oxide layer, which is silicon dioxide, that covers the gap between two N+ diffusion, and they served as the gate G. So the device parameters are: capital L is the channel length, that is the distance between the two N+ regions. Z is the channel width. D is the thickness of oxide layer. Na is the acceptor ion doping concentration in p-type silicon. So the central section of the device corresponds to the MOS diode, and the source over here is used as the voltage reference. So let us now discuss the detailed operation of enhancement mode N-channel MOSFET. Let us take the case first, that is no Vg is applied, that is Vg equal to 0. So source to drain electrodes, they corresponds to two N+ P junctions connected back to back. So here the device is off when Vg equal to 0, as there is no channel between the source and the drain. Let us now take the case 2, that is some gate voltage is applied which is greater than Vt, the threshold voltage. So this is known as the inversion condition for MOS. So if we have a large positive gate voltage, that is Vg greater than Vth, has to be applied to induce a channel below the oxide, that is a surface inversion layer, that is accumulated electrons is created. So the electron concentration in the channel, they gets enhanced by increasing Vg, and hence channel conductance can be modulated by Vg. So students, now the MOSFET enters into the inversion condition. So for Vg greater than Vt, there are various cases. Let us take the case first, that is a small positive drain voltage is applied. So here the electron will flow from S to D, that is from source to drain, through conducting channel. So here the channel acts as a resistance. That means your ID is proportional to Vd, which corresponds to the linear region as shown in this figure. As long as Vd is small, the surface potential will remain almost the same throughout the channel, that is near source and drain regions. So the electron concentration will remain same, and channel behaves as a resistor having the resistance R equal to L by sigma A, which is equal to minus L by mu n Z multiplied by Qn, where Qn is less than 0. It is nothing but the space charge per unit area of inversion layer or a channel, and Z is the channel width. Now let us take the second case, that is a moderate value of Vd is applied. So now increasing the Vd, the potential will distribute throughout the channel. So the potential difference between G and the inversion layer will be more near the source and very less near the drain. So thus the electron concentration Qn in the channel will be relatively less near D, and hence channel resistance increases. Therefore, IV curve will bend downward from initial linear variation, and this region is shown by the saturation region in this figure. Let us now discuss next case, that is for large VD. That is, if VD is further increases beyond, that is, it approaches the VD saturation. So the potential drop across the oxide near the drain will continue to decrease and may until it falls below the value required to maintain an inversion layer. That is, the width of the inversion layer, which is denoted by Xi at y equal to capital L, reduces to 0. This is known as the pinch off point, which is denoted by P in the right hand side figure. At this condition, drain gets isolated from the conducting channel by a depletion region. So the ID will then saturate to a constant value ID saturation at VD equal to VD saturation. Let us now discuss the last case, that is a VD is increased beyond VD saturation. So here ID remains as ID saturation, and the pinch off point P, it will move towards the source, and effective channel length L prime, it will decrease, which is clearly evident from the figure. However, the potential at P will remain at VD saturation, and additional voltage in excess of VD saturation will drop across the depletion region. Thus, number of carriers arriving at point P from the source, and hence current flowing from drain to source, remains constant. So, if VG or VGS increases for fixed VD, it leads to the increase in the inversion layer and thus the charge Qn. Therefore, channel resistance decreases or ID increases for a given VD. So the pinch off will occur at a higher value of VD. So let us now discuss the study of IV relationship for N-channel enhancement MOSFET. Before doing that, let us consider certain ideal conditions and the following assumptions. Number 1, the ideal MOS structure, that is, there is no charge in the oxide and no difference in the work functions of gate and semiconductors, that is phi ms equal to 0. Number 2, current flow in one dimension, that is in channel only. So no current flows from channel to gate. Next is the electron mobility in the inversion layer, that is a channel, is a constant and is independent of the electric field. Number 4, the doping in the semiconductor in the channel region is uniform. Next is the reverse leakage current is negligibly small. Last assumption is the transverse electric field, which is perpendicular to the current flow at the edge of the depletion region in a channel, is much larger than the longitudinal electric field that is parallel to the current flow. So here, let the source and the substrate are connected and consider a strong inversion condition. That means no drain current flow in a MOS, so system is in thermal equilibrium, that is Vd equal to 0. So students, let us now discuss or consider the N-channel MOSFET, whose schematic is shown in this figure, and the total charge induced in a semiconductor at Y is QSY equal to QNY plus QSCY, where Qn is the charge per unit area in the inversion region and QSC is the charge per unit area in the depletion region. Applied Vg is partly divided in oxide layer and semiconductor as Vg equal to V0 plus psi s as a function of y equal to minus QSY divided by C0 plus psi s y, where V0 is the voltage drop across the oxide layer. So in the case of non-ideal MOS capacitor with the flat band voltage VFB, equation 3 is modified as Vg minus VFB equal to minus QSY by C0 plus psi s as a function of y. Now putting the value, this equation has been termed as 3a. So putting the value of Qs from equation 2 in this equation, we get C0 multiplied by psi sy minus Vg plus VFB equal to Qn as a function of y plus QSC as a function of y. So similarly, for solving Qn as a function of y, we have Qny equal to C0 multiplied by bracket psi sy minus Vg plus VFB bracket close minus QSCY. This equation is termed as equation 4. At the onset of inversion, psi sy equal to twice of psi b. So under practical operating condition, space charge region in the MOS transistor is not in equilibrium. That is when Vd is greater than 0. So the surface potential will increase with Y due to the potential distribution in semiconductor. So if Vy is the channel potential at any point Y for a drain voltage Vd, then to a good approximation, the surface potential for strong inversion is psi s inversion Y equal to twice psi b plus Vy. Also using depletion approximation, the charge per unit area at strong inversion as calculated while discussing a MOS diode is QSC as a function of Y equal to minus QNAWM approximately equal to minus of root of 2 epsilon s QNA multiplied by Vy plus 2 psi b. These two equations have been marked as 5 and 6. Since Vy increases with y, so QSCY increases with y from S to D. So putting psi sy and QSCY from equations 5 and 6 in 4, we get Qn as a function of y equal to C0 multiplied by 2 psi b plus V minus Vg plus Vfp plus root of 2 epsilon s Qna multiplied by Vy plus 2 psi b. So consider a small element dy in the channel, and for a constant mobility μn, the resistance of small element dy of the channel is dr equal to minus dy by z mu n multiplied by Qn y. So the voltage drop across the element of resistance dr due to drain current id is dv equal to id multiplied by dr. So using equation 8, we have id dy equal to minus mu n multiplied by z multiplied by Qn y multiplied by dv. So this has been termed as equation 9. Now substituting Qn y from equation 7 in 9 and integrating from y equal to 0 to L and from v equal to 0 to Vd. So we get id multiplied by L equal to minus mu n z C0 multiplied by 0 to Vd, the integral over 2 psi b y plus Vy minus Vg plus Vfp multiplied by dV plus root of 2 epsilon s Qna by C0. This is multiplied by integral 0 to Vd of root of 2 psi by plus Vy multiplied by dV. So id is equal to mu n z C0 by L multiplied by Vg minus Vfp minus 2 psi b minus Vd square by 2 multiplied by Vd minus root of 2 epsilon s Qna by C0 multiplied by 2 by 3 multiplied by 2 psi b plus Vd to the power 3 by 2 minus 2 psi b to the power 3 by 2. So this equation is being marked as 10. Now for ideal MOSFET, remove the contribution from VFP in equation 10. So now discussing the above equation 10 in different regions or different conditions. So first region is a linear region. For small Vd such that Vd is very much less than Vg minus Vt, or Vd is very much less than Vg minus Vfp plus 2 psi b. So id is equal to mu n z C0 by L, and this id has been obtained by neglecting the contribution from Vd square by 2. So equation 10 becomes id equal to mu n z C0 by L multiplied by Vg minus Vfp minus 2 psi b multiplied by Vd minus root of 2 epsilon s Qna by C0 multiplied by 2 by 3 bracket 2 psi b to the power 3 by 2 multiplied by 1 plus Vd by 2 psi b to the power 3 by 2 minus 2 psi b to the power 3 by 2, the bracket close. id is equal to mu n z C naught by L bracket Vg minus Vfb minus 2 psi b multiplied by Vd minus root of 2 epsilon s q n a by C naught multiplied by 2 by 3 multiplied by 2 psi b to the power 3 by 2 multiplied by 1 plus 3 by 2 Vd by 2 psi b minus 2 psi b to the power 3 by 2 bracket close. Now after simplification it is equal to mu n z C naught by L bracket Vg minus Vfb minus 2 psi b minus root of 4 epsilon s q n a psi b by C naught bracket close Vd. This is equal to mu n z C naught by L bracket Vg minus Vt bracket close multiplied by Vd, where Vt equal to Vfb plus 2 psi b plus root of 2 epsilon s q n a 2 psi b by C naught. So hence by plotting Id versus Vg or small vd, Vt can be obtained from linear extrapolation to Vg axis. So for n-channel MOSFET, Vfb is small negative and other two terms of the above equation, they are positive. This implies Vt greater than 0, that is turn on voltage. So equation 12 implies that Id is proportional to Vd for small vd. So in linear region from equation 12 we have the channel conductance is Gd equal to delta Id by delta Vd at constant Vg equal to mu n z C naught by L multiplied by Vg minus Vt, and the transconductance is Gm equal to delta Id by delta Vg at constant Vd equal to mu n z C naught by L multiplied by Vd. Saturation region. Now when Vd is greater than V saturation, then at the drain and the net voltage across the MOS is less than or equal to Vt, that is number of mobile electrons in the channel at the drain are reduced drastically. This is the pinch off point. So here at the source side, we have V as a function of y to be equal to 0, Qny equal to Qn at y equal to 0. And at the drain side, we have V as a function of y equal to Vd saturation and Qny equal to 0 at y equal to 1. Now putting the source side condition in equation 7, that is for Q and Y, we have 0 equal to C naught multiplied by bracket 2 psi b plus Vd saturation minus Vg plus Vfp bracket close plus root of 2 epsilon s multiplied by q multiplied by Na bracket Vd saturation plus 2 psi b bracket close. So after solving we get 2 psi b plus Vd saturation minus Vg plus Vfp equal to minus theta multiplied by root of Vd saturation plus 2 psi b. This is termed as equation 16, where theta is equal to root of 2 epsilon s q n a divided by C0. This is equation 17. Now we'll find out VD saturation from equation 16 and substitute VD equal to VD saturation in equation 10. We can obtain the expression for ID in saturation region, that is ID saturation. However, when Na is very low and the oxide layer thickness is small, that is C0 is large, then theta is very much less than 1 from equation 17. So here the voltage drop in the oxide is negligibly small compared to psi b, 2 multiplied by psi b. So thus equation 16 becomes VD saturation equal to Vg minus VFP minus 2 psi b, approximately equal to Vg minus Vt from equation 13, as theta is very much less than 1. So putting the value of Vd equal to Vd saturation in equation 10, we have ID equal to ID saturation as ID saturation equal to mu n z C0 by L multiplied by bracket Vg minus VFB minus 2 psi b minus Vg minus Vt by 2. This is multiplied by Vg minus Vt. Minus 2 by 3 theta multiplied by 2 psi b plus Vg minus Vt to the power 3 by 2 multiplied by 1 plus Vd by 2 psi b to the power 3 by 2 minus 2 psi b to the power 3 by 2, bracket close. So this is equal to mu n z C0 by L multiplied by Vg minus Vt the whole square minus Vg minus Vt the whole square divided by 2, bracket close. So for theta very much less than 1, second term is neglected, and Vt equal to VFP plus 2 psi p. So ID saturation is equal to mu n z C0 by 2L multiplied by Vg minus Vt the whole square. So this is the square law dependence of ID on Vg, which is the same as in JFET, and it is valid for all Vd greater than Vg minus Vt. So here ID is independent of Vd. So channel conductance in saturation region, that is Gd equal to delta ID by delta Vd equal to 0. And the transconductance in saturation region is given by Gm equal to delta ID by delta Vg at constant Vd equal to mu n z C0 by L multiplied by Vg minus Vt. Thus, channel conductance Gd in linear region, that is equation 14, it is same as the transconductance Gm in saturation region given by the above equation for MOSFET. So students, let us now discuss the construction of N-channel depletion mode MOSFET. So this shows the schematic of the depletion mode MOSFET. Here the drain and the source leads, they are connected to the N plus doped regions via the N channel, and N channel is connected to the gate G via a thin insulating layer of SiO2. The N doped material lies on a P doped substrate that may have an additional terminal connection called as DSS. Depletion mode MOSFET, D-MOSFET, the basic operation. So this shows the transfer characteristics of the D-MOSFET, which are similar to the JFET. So in the depletion mode operation, we have when VGS equal to 0, then ID equal to IDSS, that is normally on condition. When VGS is less than 0 volt, then ID is less than IDSS, that is off state. When VGS is greater than 0 volts, then ID is greater than IDSS. So let us now discuss the P-channel depletion mode MOSFET. Now here, the P-channel depletion mode MOSFET, it is similar to the N-channel except that the channel is P-type and the voltage polarities and the current directions are reversed. As you can see from these characteristic curves, that is ID, it is positive for positive VGS, and here also the VGS is a positive quantity and ID shows a similar variation with VDS as that of the enhancement N-channel enhancement mode MOSFET or N-channel depletion mode MOSFET. Frequency limit for MOSFET. So this circuit shows the small signal AC equivalent circuit for MOSFET. So at higher frequency, consider a capacitive coupling between the device terminals as CGS is the MOS capacitance given by the dimensions of oxide layer ZLC, where C is equal to C0 Cj divided by C0 plus Cj and CGS equal to C0 ZL. CGD is the gate to drain capacitance, provide undesirable feedback between input and output. So consider Ft to be equal to frequency at which the ratio of I output to I input becomes unity. That is, device can no longer amplify the input signal when output of MOSFET is short circuited. So Im be the input current. So from the circuit shown above, Im is equal to 2 pi Ft multiplied by CGS plus CGD multiplied by Vg. This is equal to 2 pi Ft Cg Vg, where Cg equal to CGS plus CGD. From the output of the circuit, I0 plus omega CGD multiplied by Vg equal to Gm Vg, where I0 is the output current as shown in this figure. So I0 equal to Gm Vg minus omega CGD multiplied by Vg. So here Im is equal to I0, thus 2 pi Ft Cg Vg equal to Gm Vg. Now neglecting the contribution from omega CGD, Ft is equal to Gm by 2 pi Cg equal to mu n Z C0 Vd by 2 pi C0 ZL square equal to mu n Vd by 2 pi L square, where C0 is the capacitance of oxide and D is the thickness of oxide layer. Now here L should be as low as possible for fast switching. So students, let us summarize what we have learned in this module. First, the schematic of enhancement mode, that is E-MOSFET, was discussed. Second, the detailed operation of N-channel MOSFET was discussed. Thirdly, we studied the IV characteristics by deriving the relationship between the current versus voltage for MOSFET. Next, we studied the construction of N and P channel depletion mode MOSFET. Lastly, we studied about the frequency limits for a MOSFET. Thank you.